which one? Full screen here. What? Okay. Let's start. Thanks for waiting. Welcome you. Thanks for the opportunity to present a little bit of our insights to the project. Yeah, like already told, we are coming from the CFD world, the classical CFD world, facing different problems, engineering problems, basically. Here, down at the left, we have an optimization problem where we also quite familiar with state optimization of a pipe, where we then try to reduce, or the institute try to reduce the pressure loss in that pipe. And the design was, how does the pipe needs to look? The second idea would, of course, be multiple physical flows here with a different density. So we have water and air and the ship cruising in a wavy plane surface on wall surface, which is also quite hard numerically, and also from CFD wise requires quite some computation. And also the next one is a really like high resolution case where we like to cover cavity, so sudden decrease in pressure in order to then maybe continue with safe optimization of that propeller or other things. So basically where we see ourselves is mainly in the middle, so or in the middle of that picture. So we have industrial partner, for example, like Engis, where we have Eugene here today as well, and also two of his staff members, which maybe the interface on that side. One probable case would be the application of shape optimization on the passenger vehicle. Here we got just a reference down here on the right, where the plan was to optimize the side mirror in order to reduce the acoustic noise in the passenger environment. This could be one industrial application. On the other side, we have our academic partners, the guys from the quantum world. Here, maybe the application or the publication from the Mr. Jaksch, Kiffner, and Lübers et al., where they showed the variational quantum algorithm idea for nonlinear problems. And we are now getting at the moment in between to use MPS techniques and VQA methods in order to see the bridge between the CFD and the quantum world. Our motivation is, of course, then to first get knowledge of the QCFD part. So the Q is the main target we are aiming for at the moment, not to stand that, and to, of course, understand what is really the performance we can gain for that, advantages, and then to take that basic idea in order to address industrial problems like with high Reynolds numbers. We already learned in the first part of this this exchange today that if the Reynolds number is quite an important similitude parameter in order to parameterize or to characterize flow characteristics. And here is also something which is crucial to understand, and what we need to put effort in order to come up with high Reynolds number flows and to understand them. The idea is then first could be to have a look at banded channel flow, where we just have an inflow. It's a 2D case, go around the corner, have an outflow. It's really important here again is the Reynolds number, the Brownlee layer, and also that curving criteria or the curving characteristics. Also not that easy to get that first. Using the final volume method here is maintaining as communicated in the beginning that everything which comes in is also coming out. Which is extended, or which is the aim of our initiative, in order to come really up with a practical applicational idea there. The overall aim should then be, of course, to cover some, for example, thermal management battery system ideas, where we then have next to the velocity and pressure, we also would have the temperature, which is also another uncertainty or another variable which also needs to be covered. So our idea is to think small and to maybe learn for the big cases. So what we are doing is we try to understand at the moment the fundamentals of quantum computing. What is matrix product states? What's the language we need to learn in order to, somehow understand and communicate in that project? So what are gates? What are the ansatzes? What are the optimizer? What is that doing? And where are the parallels to the QC or to the CFD world we like to, or we know? Then we had also the chance to look quickly into tensor format representation. We see some possibilities where we can use MPS in order to come up with the quantum computing or the quantum circuits, but this is not really where we have the look into. At the moment, we more had to look into finite differencing. We started at the Schrödinger equation in order to come up with the Poisson equation, and then to evolve even further to the convective, with the convective term here in the middle, where we then can have the Berger equation with the time dependency. But this changed a little. The idea was initially to start in these cases in order to how does this polynomial interpolation method look like, what Mr. Rung introduced in the beginning? Are there maybe some similarities between the gate structure or the MPS structure, which we can then adapt to the circuits? And maybe is there, like a schemata or a building recipe where we can then link the finite volume essentials to the quantum computing essentials? So in the first attempt that I already said, we walked back from the Berger's equation, which we know from CFD. We walked back to the Schrödinger equation, what you probably know even better than we do. And we use a similar structure or similar idea here as we had in the paper from Lubash et al., which was released. And we have here the kinetic term, the potential term, the interactional term in the Schrödinger equation, time independent and nonlinear. And we solved that in the domain omega, what we took first of all just a 1D finite set. I think in the beginning we started with 4 discrete points, and now we are ramping a little bit up. But this is how the domain looks like. And we implied, of course, no boundary condition, since this was also too hard. So we went for periodic boundary conditions in order to simplify really the aim of the problem as much as possible. Stationary time already set that. And then now we started, okay, how do we now fit this framework, which is now the most simple framework we can imagine, where we have the description availability as a Hamiltonian, where Mr. Yak said this is really if you have a Hamiltonian, this might be really even more forward in order to do that. And this is where we said, okay, let's try in order to get our hands on that. So what we did is we use like a Qiskit backend, the IBM language for quantum computing. And we wrote our own, I would say, tool or solver thing around where we could really interact a little bit more and really have the stencils, and where we can involve a little instead of this online Qiskit Jupyter notebook world. At the moment we have object-oriented Python code there, where we have really QMPU object, we have an ansatz object, we have that ancilla measurement object, and we can just play around with that. We can do the measurements. We have state simulator from Qiskit available. And there's where we can, first of all, experience that problem, first of all, especially for a low parameterized object or low parameterized ansatz. It's even possible to do really a full state elaboration where we just scan all parameters of the quantum ansatz in order to get known to the topography of our optimization problem and to learn a little bit how this is looked like. And there's really a crucial point where we see that sometimes it can be non-convex, so that we have many local stationary points where the derivative vanishes, and also we have quite a complexity there. So since we do not know anything, the first shot was to use like a particle swarm optimization / Monte Carlo idea. So what we can do from CFD, we can run quite many simulations, and we also, I think, quite experienced in parallel computation. So we just thought, okay, let's use the hardware what we have and run as many ideas or as many experience in order to have an idea, first of all, of the problem that we solve. The thing is, basically, when you use a gradient-based optimization method, you're basically linked, or the initial point is quite important. It's basically for every optimization problem. Where you start determines where you end. If you're at the wrong location to start, you probably run to local minima, and then you just end up with a solution which might be optimal, but not the most optimal you can harvest in that region. So basically, there we use a Monte Carlo idea, fully parallelized. So, and then we continued with a gradient-based stochastic approach, the Adam optimization. And by this, we are able to reproduce the results which are shown in the Nubash publication. So first of all, we see here in the front, or maybe there's now the zoom thing. I can quickly move that a little. So let's put it here for the moment. So this is the minimization problem what we solved there. So we have the energy spanned up by the Schrödinger equation times the wave function, and then, as we saw on Mr. Yak's slides, times the complex conjugated wave function. Rewrite in this way. So we minimize f, the wave function, over the whole domain, which is then, and the integrand is representing, the expectation value or the weighted energy times the wave function. And hereby f is basically produced by the quantum ansatz, and f is then parameterized by a set of lambdas, which can be varied. So if we vary lambdas, we vary our f, and f is then still a space-dependent entity. And this is what we've done. So when we just take one simple discretization with 4 grid points, so we have our domain, and we separate it in 4 equal distant space points. And now we have just one lambda, which is parameterizing here this f. Then we can tune this lambda, of course, from 0 to 2 pi, and then it's just periodic repetition. And then we can first of all determine, okay, how does each of the summands introduce to the overall cost function, where the overall cost function is basically proportional to the energy. So, and here we see that the overall cost function is just spanned up by, the Laplacian k, the potential term p, and the interaction term I. So if we take the factor g equals 10 before the interaction term, we basically have quite high impact of k and p, and I is way lower. So this is why you see the green here in the bottom. And then the overall domain, or the overall parameter domain, where the parameter lambda maps now to the cost function c, looks a little bit like this. And there we see we have 2 local stationary points where the gradient vanishes, which are, if starting on the wrong initial location, which would definitely be an outcome of the optimization. And this is really crucial there. In order to obtain the most optimal point, we need, of course, to be really careful where to start and which direction to go. So if we now use the particle swarm or a Monte Carlo, we just shoot at in a discrete way at various locations and then select the best location. We, with high probability, will have a good initial point in order to start a gradient-based method in order to then come up with the right result. In this way, we are now able to just pick directly the optimal point just by pointing at it and evaluating the circuit we have there. For that lambda, we are able to reproduce exactly this wave function here written in blue, where we now have the potential, which was the x squared, so like a harmonic or x squared polynomial, which has a distinct point. So if we just have a look here, basically, so if we can imagine this interval, we have from 0 to 1, and we have our x squared basically, or something which is proportional to x squared, we can directly determine the minima, which is basically down here. And looking at the result there, if we have the domain, I think in this way we even shifted it a little. So the highest probability is at the location 2. So we have something like this, which is the suspected solution we discussed. If we now introduce the internal kinetic energy term a little bit more, then we see that the green line is way and more dominant. And here it's really hard to distinguish which local minima is corresponding to the global minima. But if you do some tries, you end up with like a more or less slightly bended curve. It's quite hard to see here on the scale, but please refer to the paper below in order to have some more insights on the approach. But this was like a major milestone where we thought, okay, we are able to at least understand and reproduce to a certain degree what the professionals from the quantum world are capable to do. And this is something we basically got an idea which direction to aim. So now can we go further? Yeah. So lessons learned, basically. What's really important from our point of view is to really know the matrix product states, which is a good language we suspect in order to transfer a little between the CFD world and the quantum computing world. Then that the quantum computing implementations regarding the variational quantum algorithm, they are not that straightforward as on the first glimpse is visible. And third, that what I already said, that it is quite a tough optimization problem since we are made non-convex. So not always is the steepest descent direction leading to the steepest or the best point. Further, we are constrained, so not all regions are really allowed to move out. And third, using this Hadamard measurement idea, we have probabilistic effects. So this is the next point, which makes it even more cumbersome. Yeah, as a reference case, our aim or motivation is to really start simple. We just had the last weeks, we just took another look to the Laplacian in order to then simulate the nonlinear Schrödinger equation in a really good shape, also on high grids. So we just tried, or we just made it to run it for 4 points. So it would be nice to see it for 16 points, for 36 points, or even more. And then is to take the whole lessons learned package to really move forward to the Burke's equation and really then to enter the arena of CFD, where we have the high difficult thing which is coming up there, namely the convective term. As I already said, which was really nice for us, is that Greta and NIST were already there, and also with the Endless guys, we have already some communications with Pierre, we had already chat, and it's really enhanced us and really helped us a lot in order that we communicated there. It is maybe also a key figure which could help. Challenges towards the industrial application of CFD, we see at the moment by really maintaining a numerical resolution with this probabilistic nature. So why not to use like a state vector simulation directly when we just use the quantum simulator and just leave aside the probabilistic machine? Furthermore, the qubit encoding. So what happens if we have more than 4 times 10 to the power of 6 degrees of freedom? So imagining one finite volume here in 3D space, which maybe comes from the battery management system, we would have 3 velocities. We would have 1 pressure, and we also would have 1 temperature available only for this simple, or not simple case, but only for this case. So if we now aim for a resolution of like a typical CFD case in, I would say, more than 1 million cells easily, then we run into some problems there, since we know from the quantum computing that of course, we always need to fulfill that normalization condition, that wave function. Let's see if I can. So we have broad side and broad inner product should be always end up to 1. So this is also something which is over behind. This is also something we see problematic there. And yeah, the last thing what we already concerned a little was the quantum ansatz. So we can use the SO4 general approach, which might be quite rich in terms of drive functions. But what if we just end up with barren plateaus there? Then we need to have like a physical motivated ansatz in order to maybe even are possible to get hold of the convective drive function setting or the dissipative drive function setting there. And this can also, in our way of looking, can also be quite cumbersome. Yeah, that's maybe first of all, like a brief overlook on what we have done. Do you have any questions on the ideas, any things we should explore a little bit more, or any basic results you like to see? If not, yeah.
Very much. I'm sure there will be some questions. I'm sure. Anybody with some questions? Yes, please, Tom.
I didn't quite understand the connection between the Barger's equation and the linear Schrodinger's equation. Could you explain that to me again?
So as we see here, you just see the kinetic term, which is basically the Laplacian, right?
Yeah.
Then, okay, we have a source term, which is also nice to have. We learn from CFD, and imagine those two, those two terms. Now we can find this again here. So basically, what we here have is also the second derivative, which is basically the Laplacian, right? Okay, we have the time-dependent term, or this instationary term there, which is giving us the evolution in time, and that convective term. So the idea is, if we're able to do the Laplacian, we already have 1/3 of the burgers, and we already have 1 step out of 3 close to CFD. So maybe
it doesn't need to be the same. I would say start from simple, as he said, and probably the diffusion term is, from the CFD perspective, the simplest term you can get. I guess also from quantum. You should be able to mimic, as I said today in the morning, a constant, which is the solution for this very trivial boundary condition scenario. And believe it or not, but we failed with this already initially. We can do, but we failed initially. And that's the only connection. And then you know, if you fail for the burgers, you might say, can you do the Laplacian, which is part of the burgers, so to say. If you can't do the Laplacian, you can't do the most simple case integrate. And then from there on, gradually ramp up, increase complexity, just to make sure that you don't mix up errors in complex problems with hidden errors that you have already inside your code. That's a very trivial point.
And this is exactly what Mr. Rung just mentioned. So what we did, we just had to look at the Laplacian. So we have the non-linear time-independent Schrödinger equation. We reformulated the optimization problem, and then basically what we did is first use the particular swarm optimization, which is Monte Carlo simulation for simplicity, up to the red line. So the convergence criteria was set to 10 to the power of minus 3 or 4 point. I can look it up clearly. Should be 2 to the power of 10 minus 4. Then we switched to the gradient-based approach, where we use the phase shift rule to manipulate the parameters. And then we went further. And what we just did here, we just got is basically 1% off a constant on 4 grid points. So just a Laplacian should lead to just a constant line in space but basically we just made it to obtain this by a lot of noise. So maybe there's something running wrong in the gradient, or we do have some wrong settings, but this was the most we got to that point, and but we try to aim even more.
That on the classical simulator or on the actual quantum computer?
On QCFD, yeah.
Honestly, if I would have been asked, this is not sufficiently accurate.
I would have thought that it
1%
must work
is
better.
not sufficiently accurate.
It's open 1%.
Open, yeah.
Over 1%.
Yeah, it should be.
But this is only for discretization of 4 discrete points. If we wrap it up to 16,
You try it.
yeah, here.
Then you go home.
Yeah, for 16.
Well, you're getting worse.
Yeah, 1%. No, yeah. 0.1% off. And yeah, what we see, the problem what we face at the moment is basically when we change to gradient-based approaches, we get still a nice descent here. So the gradient here, normalized, is still really fresh and we can really work on that. But then to a certain point, the gradient stays way less or more constant, and we have a constant fluctuation here around 10 to the power of 5 to the power of -4, which is then limiting us there in order to reduce the accuracy here even more. And
I mean, but this is on Qiskit, so you should in principle work perfectly.
we just trying to learn. If you say it should work, then we should find a bug somewhere.
Yes, it's the simulation, so it should work. So may I just ask you, unless there's any other questions? Otherwise, I still must. Yeah. But when you did this on the IBM machine, how, for instance, how did you do the different terms? Did you really all implement them one by one?
Yeah.
Okay,
One by one.
One by one with the square potential and all of that.
Yep. In this case, we just eliminated them. So for the reproducing the result you showed in the publication, yes.
You ran the whole network.
Yeah. But we run
it less than me.
We run it locally. We run it locally on our machine, so we have this in order to use really like full MPI backend and everything. We have been limited online, and we are definitely happy to share that with you. And we are via GitLab. We have a repository there, but we didn't understood basically why we couldn't make it for n equals 4, 6, 7. So this is why we really step back to what we need from CFD. This is a blessing to work. And this is where we've been concentrating heavily the last weeks. And we, made it at least in, I would say, the solutions way more converged to that actual state of 150 steps. Then after that, there's just, nothing happening. But we didn't make it to come up with a better result. So this is really fresh from the oven, and please do not, hesitate to.
My question would be, what is the order of accuracy we should get? You would expect
on the Qiskit simulator. Well, if you take the state vector simulator, you should get a perfect or nearly perfect machine accuracy result.
We do not take.
You do not take. You take
the Hadamard measurement idea, and we do 2 to the power of 18 shots, just
2 to the power of 18.
Yeah, just in order to get rid of the variance, just brute force.
But when you can switch to the state vector simulator. Do you then get perfect result?
We haven't checked, but this is the idea we have in mind, and this is be done. But
with the approach we do now, what could be the accuracy?
Well, if it's 2 to the 18 shots, you would expect an accuracy of 2 to the 9 or so. So the first 9 digits, or perhaps a bit less. But this is all just simulated, so it should be as accurate as it gets on machine precision, essentially.
There's no noise on the gates, right?
no, we do not have any noise implied.
So
I double check, but I think
this should get accurate.
2 to the 9 is 1,000.
1 over. So you should get a number of zeros there. So you should really be, pretty accurate.
So what's the origin of this? Is this systematic error?
This is the question. I think it's exactly the question. What is the origin of these oscillations? Because it looks like oscillations. It looks systematic, yes.
This is 16. Can we go back to 4?
It also,
Yeah, you have the same. The error is over.
the error is much less.
Yeah. But we also have the same effect. As you see, the derivative stays really converges to a constant normalized there, which is bad because we have still a way to harvest. So it would be nice to, since
but that should,
optimal point would be a vanishing derivative there, and this is what we like to see at some point.
you need to.
Yeah.
This should certainly be accurate.
But at least we wanted to give you some insights into the fresh from the oven
And
results.
when you do
and-
this on the actual, you also ran this on the actual IBM machine, is that true?
No,
No,
just locally,
Just
Okay, that's
on the machine.
simulating and
Also-
trying to learn from experiments.
Because I thought that this was pretty good for.
No.
Okay, any other questions then?
Yeah, sorry, but may I ask again? So, but this is the simulator of IBM, no?
Yes, we use the simulator backend and we just run it locally on a Linux computer. No
No, but then
quantum
there are
computer
errors
involved.
included, right? Because Dieter, you were saying before that there are no errors included, no? But in the simulator,
Exactly, so it should basically work perfectly, that's what I would have thought.
no, but in the IBM simulator they do include errors, right?
Yeah, but you can switch them on and off. Yes.
So
They
here,
switch them off.
so errors are
Yeah,
not.
yeah. I think you switch them off.
I hope so. I double check, but I'm
But you automatically switch, but you can switch them off.
yeah. It depends on this, but it depends on the simulator you use. I think there are a bunch of simulator packages,
Right.
and we specifically took one without measurement noise
And without gate errors.
and without, so
Yeah.
best world we can imagine.
Yeah, so then it should be fine, yes. But if you, as soon as you switch any of them on, then of course, you would expect that.
We
You
double
need to
check.
switch them on.
Yeah, I think so.
I mean,
Maybe you never switch them off, but then of course,
that's why.
if they come automatically with the arrows, then of course you would expect more to be present. But no, I mean, if you have no arrows in there, then this should work perfectly.
Okay. Yeah, we just learning. That's a good impression, and this is
So where does the
May-
noise come?
may I ask-
The measurement from?
Yeah. Let's take Felix's question first and then take
Okay.
yours online.
So the noise in the classification here, like where does that come from? Like, is that just the measurement shot noise or?
that's the question.
No, but there is no measurement shot noise if they don't.
Oh, because they're doing.
that they do
So
it.
it has to come from. Okay, that's very.
The question, does it
At least what we see is that the optimization works in the first glimpse, and then we are not able to go beyond.
But look, I mean, I think you can see basically what the Laplacian does is it shifts the function.
Yeah.
And then multiplies it together. And so when you shift the constant, you shift it, doesn't change, you multiply it together, it should give just 0, okay? Because you subtract 2.
Yeah, true.
So only the constant function will give you exactly 0 for the
Yeah.
Laplacian. And
Yeah.
so any kind of change in there does
Yes.
not. And if you don't have shock noise, if you don't have any of that
Then-
noise, then it should just be constant.
Okay. Yeah, we are not constant. We are 10 to the power 4, which is not 0.
Yeah.
Did you evaluate the objective function for a given constant value? You plug in a constant value.
Yeah, we did, right? So
What is the result of the objective function when you plug in?
Oh,
do you know?
I don't have the number. I don't have the number now. No, okay, number.
So
But
what we did is we validated at least, or we checked if our network is doing the same by introducing a Dirac impulse and the initial state just on the QMU. So without Hadamard, without the ansatz, so just QMU, and then Dirac goes in and out, got the Dirac shifted by 1 value, which was what we like to see.
should be
Then we introduced nothing, and I think the result was nothing, but I need to check that. and we introduced random noise, and not the same random noise was delivered in the output.
Should always be shifted per one.
Also the random noise.
But
Then I need to
multiply
double
with,
check.
should take the noise and multiply with the shifted.
Okay, then I need to double check. But the Dirac was looking correctly.
I think you're doing similar things.
Yeah, this. Yeah.
You have the same results.
20% as well, right? No, I think I'm like, because I'm working like right now with roughly 500 shots or something, because I don't know how they do it, but when I do 200,000 shots or something like they do, like just one simulation with the shotting takes an hour. I don't know if I use Kinski wrong, but
No, you're doing it locally on your server.
Yeah,
I
like
do
on,
too.
on the machine.
it takes a long time with
Yeah.
a lot of shots.
This runs for 10 minutes.
How many shots were it today?
2 to the power of 18, so it's like 250,000. Yeah, times 2. Yeah, 500.
Sorry, can I?
Right, there was one more question here, please.
Yes. Can I? Yeah, just quickly. So you mentioned 200,000 shots, and these are huge numbers. Just to highlight, when we go to the real hardware, our friends, if they don't charge us, they will hate us. If they charge us, we'll blow the budget. So we have to really be very, very careful with these numbers. I'll say a few things in my talk in a bit, but that's just a side comment. This is excellent to see. We have some similar simulations from the NLSC. We didn't get the noise. So do you have the circuits, the circuit decomposition you run? Do you have the gate sequence in the slide? Maybe we could, if we have a look, I could tell you where this could come in.
Right, okay.
Yeah, no, I think not the full one.
You don't have the
But
full.
as done in the publication by Lubash.
Okay. Feel free to reach out to us and Mohammed, because Mohammed is my postdoc, is in the audience doing exactly the same thing. I'll speak about it in a bit, so you guys can compare notes. I'm just saying it now in case I forget later. But I think we didn't get this one on the simulator at least. Okay.
Maybe I should add that we had this discussion in some of the group where you can basically there are these schemes that promise to improve the number of shots by a factor of 1 million or so. But that's still to be tested. But
Yeah.
that, of course, would be what one wants.
Yeah. The idea was first to just go around the issue with probabilistic effects first by using the same idea, but this is why we just increased on the local machine such a high value in order to just have it correct or like that. But of course there needs to be work in that direction.
Okay, any other questions?
Maybe,
Yeah.
sorry. So, is it possible to use another optimizer instead of Adam when you
Definitely.
will enter into this strange oscillating?
Yeah, we tried gradient descent. So if we just take the phase shift rule to compute that number of parameters times 2 plus 1 variations of the circuit, and then we have the gradient, we just plugged in the gradient directly. Same behavior, even worse. We use stochastic gradient optimization. Same, even worse. I think Adam is doing quite good, since when we have a look at Adam, we just see, so here in the lower part, we have the actual solution, which is then updated by kind of the derivative, and then also something which is proportional to 1 over the derivative squared, or 1 over the derivative squared. And this is really having us first. We have this term, and then we have a kind of momentum, which is then even pushing us more in that direction, which is quite good.
Okay, so there is no
but-
noise in Adam.
Yeah, and as we learned, I do not see any noise in the end. As we learned from our optimization in the recent years, is that also the same when you enhance the problem even more and make it more complex and more advanced. Of course, you get nice side effects, but basically optimizing it gets more and more harder. So of course we could use an LBFGS method, so where we just update or we have an iterative prescription in order to come up with a Hessian, or we could use some totally different ideas. But this is why we just went first for this particle swarm here in the beginning, where we have a good polarization, where we do computations fast in order to come up with a Monte Carlo initial guess, and then to use like only the first order method to then work on that problem, because it's just simple and does what it should.
It's definitely something to look into. Yes, Tom?
I think I'm really, it might be a really stupid question, but if you go to the Laplacian side,
To the result. Yeah.
so the solution to this is a fine wave. Solution to
Constant.
is a fine wave solution.
Constant.
E to the I. Wait, the sine wave will solve the problem. E to the I square root of B.
Yeah, except he wants to minimize, and so the plane wave is the minimal energy is the
Yeah,
constant.
okay. Yeah,
We
yeah.
also time
With
independent.
E equals 0, it's
And of course, one thing that could happen is that you get into some kind of weird jumping back and forth between
so,
this.
so yeah, what I see here is this oscillatory behavior exactly.
Yeah. So when you look here from one iteration to the next, how does this change? Does it change anymore? Or does it?
Here, we see it's like just noise. So basically,
Yeah,
that's
but
the
this
thing.
one, does this change? And is this
Answer. Yeah.
the answer stays?
Does the answer stay, or does the answer move in a sinusoidal
No.
manner that you see
The answer
continuous
stays.
weak
Yeah.
sinusoidal?
It just maybe evolves and maybe compresses and
You see amplitude
change.
just by the
But
phase
yeah,
changes.
yeah, correct.
One quick
But-
question on
We definitely learn from that. We have a look into that. Definitely. Yeah. Some questions online? Yeah.
just quickly. Did you guys try to calculate the cost function with the directed cheat way, not via the ancilla? And if so, I think it was also in the appendix of Lubach et al. And if you did you get the noise there too, or not?
Yeah. This is what they also proposed here locally. That this is something we also had on our list, but we didn't made it to this meeting. We just put up the results in order to show you really like the latest
Yeah, that's
level.
fine. That's fine. No, I'm just checking whether if you got the noise there too, then it sounds problem with the implementation.
Yeah,
Because
definitely.
the cheat way
This-
definitely works. We have tried it and it works.
Yeah.
Okay.
Thanks. We have that on high priority now.
Good job.
Any other questions? Well, if not, I think we need to move on.
Yeah.
Thanks. Good call again. What the reason?